Okay. Uh, in this set of slides, we're going to look at topic 8.2 in the IBHL curriculum. Topic 8.2 is the second half of the applied physics unit, which in this case is taking a look at how our understanding of thermal energy can be applied to the Earth system to figure out how, or to understand how the Earth maintains a near constant temperature as a result of energy inputs from the sun, energy losses from radiative cooling, and the importance of the atmosphere in the greenhouse effect. Uh, I think about it in two halves. The first is some physics that is related to what we've studied in topic 3, and also in topic 4 for light, but extends it a little bit to talk about energy transfer by radiation. So this is some new physics, and then in the second half, we'll apply that to the Earth system. The big idea here is that we're going to treat the Earth as a black body radiator and the atmosphere as a gray body. Lots of new vocabulary there. In the first half, we'll try to understand what this means by a black body radiator, as radiation is one of the 3 forms of heat transfer, the third of convection, conduction, and radiation. So we're going to be looking at that black body radiation here. We'll also look at some associated physics, like how with radiation on a spectrum from a hot object, there's a peak intensity or a peak wavelength where the intensity is greatest at that wavelength, and there's a pattern to that. And this will involve doing some problem solving with the Stefan Boltzmann law and with Wiens Displacement Law. As a quick reminder, these are some things that we're going to pull in from topic 3. We have this idea of an object has an internal energy associated with it. And the internal energy is the sum of the random kinetic energy of particles, the motion of them. In this case, we have like a liquid represented here by this atomic spacing, and those particles are all moving. They also have an attractive force between them because they're charged objects, and that attraction means that there's a potential energy as well. And when you add up that kinetic energy and that potential energy, you get the total internal energy of the system. Temperature is, as we know, a measure of the kinetic energy, and so it's a partial measurement of the internal energy, but not a complete one. As long as we don't have changes of state, we're going to be in pretty good shape thinking about how if a temperature rises, the total energy is increasing. If the temperature decreases, the total energy is decreasing. Second thing to remind yourself of is that when we talk about heat, we have heat as a transfer of energy as a result of difference in temperature. It takes 3 forms: convection, which is heat transfer by mixing; conduction, which is heat transfer by direct contact; and radiation, that is heat transfer by electromagnetic radiation or light. Things that are a little bit tricky here. Heat has the units of energy, so it has units of joules, but it doesn't represent energy that is located in any place. It's a transfer. So you would see, for example, when this poor boy puts his hand on the iron, his hand has heat flowing into it, and the iron has heat flowing out of it. So we would see the high temperature iron and the lower temperature hand, leading to a transfer of energy from the iron to the hand. And the same thing happens when you have mixing. The same thing happens when you have radiation. So heat. So heat, temperature, and internal energy. The first form of energy transfer that's probably the easiest one to understand is conduction. With conduction, we're thinking about that transfer of kinetic energy. So we're not thinking about changes of state here, but we're thinking about kinetic energy moving from one object. In this case, I'll think about this object at temperature T1 that's the hotter object on the left, and then the cooler object T2 on the right. And the very fast moving atoms or molecules inside of object 1 come into contact with the cooler or slower moving molecules of object 2. And the collisions between one object, or the atoms in one object and the atoms in another, leads to the transfer of kinetic energy. And that's that heat flow that we get here. We generally model the contact between objects at two different temperatures, in this case T1 and T2, as having some sort of effective cross-sectional area and some sort of effective separation. It's never going to be perfectly easy to build the model for a particular system. Like if one hand is hot and one hand is cold, what do you call the distance between those? The area of contact is maybe pretty easy to think about. Maybe it's the surface area here. But if they're touching each other, what is that distance? Maybe you think about it as like the place where the temperature remains roughly constant, maybe at the core of my hand and the core of this hand, are where you have T1 and T2 staying constant, and L is the distance between them. So modeling this is a little tricky, but when you do, the model that works well is that the rate of transfer of heat, Q over T, or the heating power, right, because that's energy per unit time, is proportional to, so we have a constant of proportionality that has to do with the material that makes up that bridge. The cross-sectional area, so the heat will be, is proportional to cross-sectional area, inversely proportional to the separation, and proportional to the difference in temperature. Nothing actually too tricky here, and if you nudge this a little bit, you'll probably see some similarities between conduction and the power transferred and the work that we did with currents and voltages moving through resistive materials. So you kind of see a constant of proportionality, a cross-sectional area, a length, and Q over T is the heat per unit time, but you could also think about that as maybe charge per unit time. And you would say then, what's this delta T representing? That temperature difference would be sort of analogous to a potential difference between the two. So this model here is very similar to the model that we have for ohmic resistors. It's very similar to the model that we have for the flow of liquid through friction, linear friction systems. So a pretty simple or a pretty straightforward relationship to apply to this. And of course, it's a model, so it works well when it works well, and it doesn't work well when it doesn't. One of my favorite places to apply this is to think about the design of windows. In our country, Malaysia, there's not a lot of need to design windows particularly well in a very temperate climate. But if you have windows in a cold weather climate where the temperature inside, you need to maintain that at a warmer temperature than outside in order to make a house habitable, window design can be really, really important. And one of the things that people will design, I got to shrink my head a little bit here, are double pane windows. And instead of a single pane of glass between an indoor temperature that is warmer and an outdoor temperature that is cooler, you have two panes of glass separated by a small air gap or a vacuum even. And these windows become much, much more insulating than even, say, thickening up this glass. So a major source of heat loss from a house is through the windows. In this case, they have a thermal conductivity. That's the value K from our previous slide, the thermal conductivity of 0.84 joules per second per meter Kelvin. Assuming a temperature difference of 3 degrees Celsius between the air inside of the window and outside of the window, calculate the rate of heat loss through a 3.2 millimeter thick glass window with dimensions of 2 meters by 1.5 meters. I'm going to let you pause for a second to do that simple calculation. Coming back, if you got stuck on this, the likely place that you got stuck was just interpreting things. The L here is the separation of the two temperatures, which we would consider to be maybe the thickness of this piece of glass. And we have to note that the units here are millimeters, so we're going to have to put a power of 10 to the minus 3 on that number. When you do, I should have probably written this number down, but the value that you should get is about 2.4 kilowatts for the energy loss. And a 2 meter by 1.5 meter window is pretty large, but that's a lot of energy being lost through the window, almost the same as having a hairdryer turned on if you're talking about trying to maintain that temperature difference. Let's compare that, and you can redo this calculation with a double pane window that takes advantage of the less conductive properties of air. Actually doing this calculation for a double pane window is difficult because you actually have heat transfer from inside the house from one side of this pane to the air, from one side of the air to the other, and then from the air through the pane of glass. But I think we can get a pretty good estimate if we assume that the temperature difference is almost all across the air. That's a pretty good assumption because air transfers heat so poorly that the glass will almost completely warm up on the left and cool down on the right, and the temperature difference will be maintained across the air. So let's find the rate of heat transfer across this, say, 2 millimeter air gap with the thermal conductivity of air of 0.023 joules per second meter degree or Kelvin. I'll pause for a second and then give you the answer. Okay, coming back, you should see that that heat transfer rate is about 0.1 kilowatts. So compared to the 2.4 kilowatts of a single pane window, adding 2 panes of glass with that, but mostly the air gap, results in a factor of about 25 reduction in the amount of heat transfer. So if you ever go to a cool climate, you'll see double or even triple paned windows in an attempt to turn like a hair dryer's worth of heat loss through a window down into something like a light bulb's loss of heat through a window. The second form of energy transfer that we look at is called convection. We're not going to end up having an equation for this one because convection becomes much more complex to study because it's the exchange of heat by the mixing or the exchange of particles. Rather than in conduction, where we think about the hot particles bumping into the cold particles so that this is a transfer of energy mediated by collisions. Convection is energy exchange by mixing up the particles, as if the hot particles that make up my hand on the left and the cool particles that make up my hand on the right just were to swap places. So the faster moving particles from this hand turn into the particles from this hand, making this object warmer. Convection, therefore, only occurs inside of liquids or gases, which can mix. Solids don't mix particularly well. And we have hotter particles entering the colder system and colder particles moving to the hot system. Convection can be forced or it can occur naturally. With natural convection, you sometimes end up with these circulation currents. In a pot of water here, the heat underneath the center of the pot causes the density of the water inside to reduce slightly, possibly even to boil, causing it to rise upward. As those hot water molecules rise, they push water upwards, and that replaces the water, and gravity pulls that cooler water from the top down, allowing it to circulate. So pots of water boil quite evenly because convection currents tend to mix the water very evenly. So you don't get hot water on the bottom of a pot and cold water on the top. The temperature in the pot is almost always pretty stable. The same thing can happen in air. If you have a heating system that involves radiators, radiators are often located close to the ground. Air rises near those and then falls in a different part of the room, often close to the windows, which, as we just saw, tend to be colder in the winter. So that's occurring due to two things. It's the changes in density that result from heating and gravity's effect on high density or low density fluids. A great video to check out, and you can see the URL here, or you can just Google boiling water in microgravity. You can actually see what happens if you take away gravity from the process of boiling. The images here will show you, but the video would be much better to watch. On Earth, what you see on 1G, the boiling involves mixing, and you get very small bubbles that circulate inside of a container of water. If you go into space or microgravity, then the convection currents don't get set up naturally. The heating that's taking place from the bottom causes the water to boil close to the bottom. But because low density gas doesn't rise in gravity because there's no force, no net force pulling low density upwards and high density down, that single bubble of gas just expands inside the bottom of the pot. So convection currents that take place because of gravity can disappear, and you get a very dramatic boiling effect here where you get this bubble just goes like boom. So I recommend watching that video. The last one, last form of energy transfer that we'll look at, or heat transfer, is radiation. Convection and conduction require matter to transfer heat, but light can also transfer heat without any matter at all, because light doesn't require a medium to move through. This is going to be the one that's most important for us in the second half of this topic, because we'll be looking at how the sun heats the Earth through radiation and how the Earth emits energy into space through radiation. Experimentally, we find that the rate of heat loss from a surface is proportional to the square of the temperature squared. So really, really strong dependence on temperature. Square of the squared is temperature to the fourth for the rate of heat transfer or heat loss. You can compare this to the expression that we had for conduction, and the rate of heat transfer for conduction was proportional to the temperature difference. Here, the energy that's lost by radiation depends on the temperature to the fourth, so a much, much stronger dependence. The proportionality here is similar in some ways. So we have E, a constant of proportionality that's known as the emissivity. It's a property of that surface. A, of course, is the surface area. And then the Stefan Boltzmann constant is a small constant that helps to take that T to the fourth in Kelvin and bring it down to the reasonable size numbers that we need for energy transfer. Emissivity is the way that we describe the very, very complex nature of radiation in a simple way. Emissivity is a value that goes between 1 and 0, with 1 being a very emissive object that emits and absorbs radiation very effectively. Poor emitters have values that are closer to 0. So a perfect mirror that doesn't absorb radiation and doesn't emit radiation would have a emissivity of 0. We call objects that are good emitter absorbers black bodies, and poor emitter absorbers are white. That helps to keep things straight for, like, say, things that you find on the surface of the Earth. Black tarred roads have very high emissivities, so they get very hot when they're exposed to the sun, and they also radiate a lot of heat outwards, so you will get hot if you stand on them. So black has an emissivity near 1. Water also is a relatively black object. On the other hand, snow or ice is a relatively poor emitter. Snow takes a long time to melt because it doesn't tend to absorb, it tends to reflect light, so heat doesn't enter it particularly well. But it does make for a good insulator. So if you were to build an igloo or a snow fort, you can stay insulated against radiation quite well because it doesn't allow that transfer of energy. These are empirically found numbers, and they're not perfect. Again, this is a simple model for radiation, and it doesn't even account for the fact that different colors of light have different rates of energy transfer. But it works reasonably well for broad spectrum light. Speaking of broad spectrums of light, I want to take a look for a moment at what we would call the spectrum of a black body. You will probably be calling back into mind what we looked at in topic 7 when we were studying the bright line spectra of individual atoms or molecules. We compared that to the spectrum from a hot filament light bulb or from the sun, which was continuous and gave all colors of the rainbow. I'm going to go over to this simulation here to talk so that we can see some of the changes that take place. It's going to take a second to load. I would recommend that you play around with this. So what we have available to play with here are we have the temperature of the object. It's written in Kelvin, so we have the temperature of the sun here at about 5,800 Kelvin. On the left, we see a graph that shows the wavelength of light. The rainbow that shows up here is showing the part of the spectrum that is visible light. Higher energy light is over here to the left. Lower energy infrared and radio waves are over to the right. And on the vertical axis, we have the spectral power density, a pretty complicated expression that talks about how much energy is radiated at each particular wavelength from each particular square meter of our hot object. You can think about it as saying, how much of this color of light are we getting in terms of the energy that it carries? Not in terms of the number of photons, which is a different thing, because as we know, the photons of high energy light carry a lot more energy than the photons of low energy light. Of high wavelength light. So what happens with this spectrum? For our sun, we can see that there's a peak here, that most of the light is in the visible part, or the most intensity of the light is from the visible part of the spectrum. That very, very peak here might be right around 500 nanometers, which is right on the sort of blue-green border. So our sun is considered a blue-green star. But there's a whole lot of energy that also comes in the infrared part of the spectrum. So over here, the area under the graph here is the energy associated with the infrared part of the spectrum. And a small amount is coming in the ultraviolet as well. At the highest frequencies, the lowest wavelengths, there isn't any energy that we see. So what's going to happen if we change the temperature? First, let's go down to something like a light bulb. So the light bulb that we looked at in class was at a temperature of around 3,000 Kelvin. We're going to take a look at two things here, two big things that we notice. One, how much less energy there is present. Not a big surprise, because remember, the energy transfer goes as T to the fourth. So if we go from around 6,000 Kelvin to around 3,000 Kelvin, we've cut the temperature in half, but that means that the rate of energy transfer has gone down by a factor of 2 to the fourth, or 16 times less energy transfer. So that's why I'm going to need to really zoom in here to see this spectrum as opposed to the spectrum of the sun. Right, so I'm going to end up clicking twice so that we see that decrease here. The other thing that we'll notice is that the peak now from the light bulb shows up inside of the infrared. Most of the energy is in the infrared part of the spectrum, and only a small amount of that energy is in the visible part of the spectrum. Connecting this back to topic 8.1, we saw how a light bulb was really only about 10%, or an incandescent light bulb was only about 10% efficient in producing light energy, and most of the energy was useless to us for the purpose of a light bulb. Here's where we see that. So we have the largest part of the spectrum is in the infrared, very difficult for us to read with. Dogs do a little bit better, but a small portion of it is inside of the visible. Going down a little bit further, so I'll take a picture of this one. Going down a little bit further, we can get to the temperature of the Earth approximately. We'll need that later, at around 300 Kelvin. So now we've gone from 3,000 down to 300. So we've gone down by a factor of 10. And with that T to the fourth, that means that we're going down by a factor of 10,000. And so we have to go boom, 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 boom. We still don't see anything. Why? Well, because over here, that peak has moved all the way over deep, deep, deep into the infrared part of the spectrum. I'll zoom in again to just sort of show you where that peak is relative to the visible part of the spectrum, which of course makes perfect sense because we think when the sun is on the other side of the planet at night, if you open your eyes, it really doesn't matter how wide you open your eyes, the Earth does not emit light that we can see. There's no light in the visible part of the spectrum. It's all deep, deep in the infrared. We can zoom in, or we can zoom out again here to kind of see what that looks like compared to the light bulb, compared to the sun, right? And it's just orders of magnitude smaller energy transfer and much, much, much larger wavelength for that peak emission. One last thing to keep looking at this is we can go to a higher temperature star. Our sun is not the hottest star in the universe. So we can go to, say, Sirius A. Where did it go? All right, let's start zooming out again. There's our new red curve comparing to the sun. We're going to have to come over here into the visible part of the spectrum, still zooming out. This dotted line is our sun. There's the Earth. And now here's Sirius A, which is peaking in the ultraviolet. So you still have a large part of the spectrum visible. You can obviously see this in the night sky, but it actually sends out more of its energy in the ultraviolet. Right? And that's because its temperature is about 10,000 Kelvin. So compared to the sun, about twice the temperature. And so we see about 16 times more power emitted by Sirius A than we do with the sun. Again, exploring that to have a good understanding of the spectra is worthwhile. So I'll let you keep playing around with that on your own. Apart from the fact that we see we use that to illustrate the T to the fourth dependence of energy transfer, that the area under that curve scales as T to the fourth. When we double the temperature, we get 16 times the energy transfer. We also saw that the location of the peak wavelength changed. Wiens Displacement Law is a expression that gives the peak wavelength for emission for a particular temperature. It's a pretty straightforward one. It just shows that the peak wavelength is inversely proportional to the temperature in Kelvin, of course, and it's just a constant divided by that temperature. So enough measurements of where that peak is. In fact, you could gather that data from the simulation if you wanted and fit it, and you find this inverse relationship for the peak wavelength of these, what are called Boltzmann-like spectrums or black body spectrums. And of course, the other one that we talked about was the power per unit area. The spectral power density is proportional to T to the fourth. So those are the two big takeaways that we have from looking at black body radiation and the black body spectrum. An application of this, you can look at the sun. So the surface of the sun is at a temperature of roughly 5,500 degrees Celsius and has an emissivity of approximately 1. The sun can be treated as a black body, in other words. The radius of the sun is approximately 7 times 10 to the 5th kilometers. Using the expressions from the last couple of slides, can you find the rate that energy is leaving the sun through radiation? And can you figure out what the peak wavelength value is? And I'll pause for a moment before I give you those numbers, or you can pause for a moment. Okay, coming back. So you actually had seen some of these values in the simulation. The rate at which the energy is leaving the sun is about 4 times 10 to the 26th watts. There's a good chance that your power of 10 may be off by a little bit. Recall that in order to find the surface area of a sphere, you need to use the expression 4 pi r squared. And the distance here, since it's in kilometers, really should be written as 6.96 times 10 to the 8th meters when you're using that. So the surface area of the sun is going to have approximately a power of 10 to the 17 or so. And then, of course, if you're still off by just a small amount, it's possible that it was because you use the temperature in Celsius. You need to make sure that you use the temperature in Kelvin, so that'll be closer to 5,800. So you can check that should be 3.8 times 10 to the 26th watts. An absolutely unthinkable amount of energy leaving the surface of the sun, which is why we don't go there very often. The peak wavelength we saw in the simulation was around 500 nanometers. Wiens Displacement Law would give you that as well. Again, you need to use the temperature in Kelvin. So temperatures in Celsius, just like in topic 3, should almost always be immediately converted into temperatures in Kelvin. When we try to apply the radiation expression to the loss of heat from an object, we need to think about not just how much energy is leaving the surface of our object, but we also have to think about how energy is entering it, because this can be a dynamic equilibrium. Your body is at a relatively high temperature, and you are pumping energy out through radiation every time you just sit and rest. But because you're usually surrounded by an environment that is also at that same temperature, energy is radiating into your body at an equal rate so you can keep it a constant temperature. This is particularly true if you're wearing clothes, because that keeps the clothes are at about the same temperature as your body. And so they radiate energy back to you so you don't lose any heat through radiation. Objects gain and lose heat in approximately the same way, especially if the environment is at a close temperature. Can be different if there are big differences in temperature. But they gain and lose heat in approximately the same way. So you make the assumption that the emissivity will be the same for heat loss from an object and for the energy absorbed from the environment. So then the net flow of energy, not the flow out or the flow in, but the net flow would be the flow in this case, the emissivity times the cross-sectional area times the Stefan Boltzmann constant times the environment's temperature to the fourth, minus the flow out, which would be emissivity, area, Boltzmann constant, times the object's temperature to the fourth. A good place to think about this might be to think about what happens when you put a room temperature pizza into a hot oven. So in this case, the environment would be the environment of the oven, which you've prepared at a high temperature. Maybe it's at, say, 400 degrees, I guess it wouldn't be 400, maybe like 300 degrees Celsius or about 600 Kelvin. And the pizza at room temperature would be at around 300 Kelvin. So the flow of energy into the pizza you could find by taking that 600 Kelvin to the fourth and subtracting 300 Kelvin to the fourth. And of course, since 600 is twice 300, you'd have 16 times larger value here. So it's almost like the radiated energy from the pizza that where its energy loss is negligible compared to the energy that's flowing in from the environment. I don't know what the emissivity of a pizza would be. Probably safe to do it about 0.7. The one that I'll have you do is actually the way that you cool down when you're sitting in a cold locker room. So if you think about not having clothes on your skin to help insulate you, we can have an athlete cooling down in the locker room. You've got dark walls at a temperature of about 15 Celsius. And we can think about the loss of heat through the skin at a temperature of, say, 36 Celsius with an emissivity of 0.7. And we can take the cross-sectional area of the body, like all of your arms and legs and chest, to be 1.8 cubic meters. So estimate that loss of heat. I'll pause for a second. You can pause for a second. Okay, coming back. Biggest mistake that you can make would be to use these temperatures in Celsius instead of in Kelvin. But if you change them to Celsius, you'll have a little bit over 300 Kelvin and about 290 Kelvin here. And the rate of heat loss would be about 160 watts, which is like enough energy to power several light bulbs. So this is why you would cool down very, very, very quickly if you are standing in a cold environment. And why clothes are such a useful tool for humans, because they can cover your body with a radiator that's at very close to your body's temperature, and they can keep you warm. Always a little bit important to just throw this slide in here. Seasons on Earth are one thing that are poorly understood by many people. We sometimes think that the most common misconception is that the summer happens when the Earth is closest to the sun, and that winter occurs when the Earth is furthest from the sun. But of course, those of you who've traveled to both sides of the equator know that when it is summer in the northern hemisphere, it is winter in the southern hemisphere, and that the real reason for the seasons is that the Earth's axis is tilted. And during summer in the northern hemisphere, this northern part of the Earth receives more direct and more total sunlight, which causes the northern half of the Earth to become warmer during the months of May, June, July, and August, whereas the southern half of the Earth is generally cooler at that time. And then, of course, as the Earth comes around to the other side of the sun, in the southern hemisphere, it's summer, and in the northern hemisphere, it's winter. Of course, where we are, near the equator, very subtle changes in temperature from throughout the year. We'll look at the greenhouse effect in our next section. So just to check that you've gotten everything that you need to from this video, you should be able to discuss the nature of convection, conduction, and radiation, specifically to be able to describe the pattern of radiation from a black body, both in terms of where its peak intensity would be from Wiens Displacement Law, and the total amount of energy emitted from the Stefan Boltzmann law, the T to the fourth law. And then there are a number of problems that you can solve with Stefan Boltzmann and Wiens Displacement Law. I don't think IB actually asked you to do any work with conduction with that first expression that we used, but it's a nice one to know about anyway. Okay, thank you very much.